Okay, recording. Nice. Yeah. So again, today is about section analysis. So today is more technical, you can say, than like last week. Last week we just covered the steps on how you design the concrete itself. Now we actually start to check lah. We haven't designed yet. Today is just checking. Yeah. Yeah. Basically getting the moment capacity of the section. That's our end goal. Okay. So as usual, I'll start with a little bit of theory. So yeah, so when you hear the word reinforced concrete, right, it's basically concrete which is reinforced by steel. So I think there's a common knowledge. Yeah, so yeah, just basically concrete and steel. Why do we add steel, right? It's actually simple also. Concrete is strong in compression only. Okay, compression only. So that's why if you see, right, if you put a load here, the upper part will have compression, the bottom part will have tension. It's like bending, like something like this. Yeah, so the bottom part is in tension, the top part is in compression. So what we do is basically we add steel. So instead of like breaking directly, the steel will hold the concrete together. So it will try to resist the pulling action basically. That's why we have steel. Yeah. So yeah, that's why we add steel to concrete. So we have a few assumptions when analyzing steel and concrete. So first things first is concrete tension is neglected. Um, concrete actually has a very little tension strength. Yeah, there's a very little tension strength, but we would like to ignore it because one, the calculation is simpler, and two is because um, it's more conservative. Yeah, so we assume concrete doesn't have any tension one. Yeah, so that's our first assumption. So for the second assumption, we assume perfect bond. So what this means is, so let's say you have a section, right? Yeah, like a concrete section, something like this. This is the side view lah, basically. So this one is the steel. The whole block is concrete. So if you pull them, so let's say you pull the concrete by this much, so it will expand, right? If you pull it, the steel will also expand the same amount. So that's our assumption. In reality, of course, there's like a little bit of slip, but we assume when analyzing, there's a perfect bond. So the strain are the same. So the strain of concrete is the same as the strain of steel at one point lah, at one point. It's basically saying, yeah, how to say? Okay, let's say we have bending lah. Let's say we have bending. So if you have bending, the strain would look something like this. The upper part is again compression, bottom part is tension. So the concrete will expand like this lah. It's a bit hard to visualize. So the top part will actually compress. The bottom part will actually expand, something like this. Is a bit exaggerated, but basically saying that since the steel is here, it will expand by the same amount. So like this. Yeah, it's basically saying when you pull the concrete, the steel also gets pulled, yeah, by the same amount. Lastly, we assume that plane sections remain plane. So imagine bending, right? Imagine bending. So let's say this is your section. If you bend, right, it will look something like this. Something like this. My drawing is not that good, but it's basically saying the rectangle stays a rectangle. That's a simplest way to say it. So we have three assumptions. So one, concrete tension is neglected. Two, perfect bond. And third is plane section. Yeah. So these are all the theories so far. Any questions? Okay, so if not, then it's okay. Then we'll go to the next one. This was asked in the 2020 quiz. Yeah, just in case you're wondering. Yeah, so the next part, now we go to the values. So just now we covered the theory. Now we go to the values. So let's start with steel first. If you notice, I've been talking a lot about stress and strain in this topic. So this one is the strain. Then we have the compression and tension, which is basically the stresses. Okay, for steel, I think you've seen this in MOM. So I'll give you a little of review. So initially, when you pull the steel, the stress is proportional to the strain. So by how much you pull, you can multiply it by the Young's modulus. So it's basically this lah. So the stress is, okay, Young's modulus is stress over strain. So the stress is just basically, yeah, Young's modulus times strain lah. So that's for this section. But then we have this turning point called the yield strength. So it's basically after this point, steel becomes plastic. So when you pull the steel even more, it goes curvy, you can see. Like the graph is not proportional. And of course, since it's plastic, it doesn't go to its original shape. Yeah, but the point is, after the yield strength, the stress is not proportional to the strain. So it looks something like this. But engineers like to simplify things. So this is the actual graph, but the graph that we will use, right, is actually something like this. So initially it's the same, it's like a straight line. Then it goes to the yield strength. Then we just assume the next is just a straight line. So it's way simpler for engineers to design things. We just need to consider two lines. So it's basically saying, okay, so this one is the yield strain. This is the yield stress. Or, okay, we can say it's a sigma y, or we can also say fy. It's both means the same thing. Sigma and f is the same thing. So what does it mean? Let's say you start with a steel like this much, and then you pull it, let's say. If you pull it this much, so let's say something like this, and like this difference side, let's say this one is less than the yield strain, then the stress, again, the stress is still proportional. So if it's less than the yield strain, the stress will be, again, it goes back to this. Stress is just, so the stress of steel is just the Young modulus of steel multiplied by its strain. So that's for this section. But for steel that you pull very long, right? Then, let's say this is the steel, again, this is the one that you pull. Let's say this is strain. So if the strain is more than the yield strain, then if you notice, it's a straight line. The strength is constant. So no matter how long you pull, right, as long as it's above the yield strain, the strength is constant as yeah, the yield strength. So the stress is just the yield stress or yield strength. Yeah, so there are two parts. So the turning point is EY. Yeah, epsilon y. What's it called? The yield strain. So what's the yield strain? So based on Eurocode 2, the yield strain is 0.00217. So this is a value that you need to put in your cheat sheet. Okay, it's basically saying if you pull the steel, if the strain is less than this value, then the strength is this. Yeah, basically this one. So if it has not yielded, then that's the strength. It's basically this line. While the other one, if the steel has yielded, then it reaches the yield strength, which is in Eurocode, it's 0.87 FYK. Yeah. So what's FYK? FYK, let me check first. I think there's a fixed value for FYK. Sorry, FYK is the steel grade. Yeah, FYK is still the steel grade. Yeah, this one is the steel grade. So sometimes you hear like grade 500, grade 450. So that's the FYK. Yeah. So that's for steel. So just two lines. So before yield strain or after yield strain, that's the strength. Then let's go to concrete. So concrete is much simpler. Again, it doesn't have tension. So if you have a section, so let's say this is your section, and you have pure bending. So pure bending, something like this, let's say. So the moment goes something like this. So the upper part will be in compression. So this is the strength of the concrete in compression. If you notice, the bottom part, there's no strength because it's tensile. Yeah, so this one is, there's nothing lah, basically in the concrete. While this one, they have like a graph lah. So unlike steel, you already know there's no two cases lah. There are no cases. It's always 0.0035. This is the failure in compression for concrete. So if you compress the concrete and it reaches 0.0035, right? It just crushes. Yeah, so if you have a concrete, something like this, then you push it, something like this. If this is bigger than 0.0035, right? Then the concrete crushes. Yeah, so it's something like that. While the stress is also, there are no two cases. The stress is just this. So FCD, which is the design stress, is 0.567 FCK. So again, FCK is the grade of the concrete. So yeah, this is like the explanation lah. So sometimes they will give you, okay, concrete of C25/30. That means the strength is 25 MPa. You take the first number. So just for your information, the first one I think represents the cube strength. Well, the second number I think is the cylinder strength. I might be wrong. I might flip the two now. Cylinder strength. So this one is in, I think we did this in our lab. So the cube strength is basically the one you have the cube and then you just compress it until it fails. That's the cube strength. While cylinder, you do the cylinder. Something like this. Yeah, so yeah, we use the cube strength. If I'm not wrong, I often flip the two. So yeah. But basically just take the first number. So that's the stress in concrete. There's also one thing to take note. So if you notice, again, the bottom one doesn't have tension because we assume it's zero. For the compression, the stress actually looks like this. In real life, it looks like this. It's a curve. And again, engineers don't like curves. We want like very simple calculations. So instead, we assume it to be a rectangle. So it's way convenient. And the rectangle is, I don't think it's written here. It's written in the next page, but I'll just write it here. It's 0.8x. X is the neutral axis. I'll explain on this later. Yeah, but we assume that the compression strength of concrete is just 0.8 of the neutral axis. Yeah. So, any questions so far? I think the one which is a bit more confusing actually is the steel. Okay, so if no questions, you all can type in the Zoom, by the way, if you don't want to talk also can, yeah. Or you can watch the recording first and ask me in the Telegram also can. Yeah. So with that, clear, we can actually start with the actual section analysis. Okay, so for today, we will do beams. So it's basically in pure bending. So again, I'll do a little bit of MOM recap. We have something called the neutral axis. So what this is, so okay, so this is the section. This is the cross section to be exact. So the section will be bent this way. So the upper part is in compression, the bottom part is in tension. This one is called the sagging moment. So actually the section is like this. Like this. This is pure bending. And something like that. Yeah, so this is this. Yeah. So what's next? Yeah, so this is the strain. This is the strain graph. This is the stress graph. So let's explore this first. So first, let's explore the strain. So in MOM, they have explained about neutral axis. So it's basically the point or the level where the strain is zero. So it doesn't get pulled, it doesn't get compressed. So if you notice above the neutral axis, so this part, they get pulled. Sorry, they get compressed. The bottom part gets pulled. Yeah, so that's the strain graph. The stress graph, if you notice, there's a few components. It looks intimidating at first, but it's actually quite simple to read. So remember, the steel is the one handling the tension force. So we have FST, for the force of steel. The force of steel in tension. So F force, S steel, T tension. Yeah. So if you notice, this one is tension, this one is compression. So this is tension, this one is compression. So yeah, this is the first component. The second component is usually the concrete. So this area. So again, the area is how much? It's 0.8 multiplied by the neutral axis. So if the neutral axis is this much, it's just basically 0.8 of it. Yeah, that's our strength of concrete. And if you remember MOM, you can, so if you have an UDL, right? Okay, let's say you have an UDL, and like this, you just take the middle. We can represent it as one force in the middle, something like this. And how big the force is basically just the area. Yeah, so it's the same thing here. So this is the strength of the concrete, but sometimes we just represent it as one line, FC, the force of concrete in compression. Yeah. Lastly, sometimes if the design is not enough, we have the compression steel. So this one is FSC. So the force of steel in compression. Force, steel, compression, FSC. Yeah, so it's located here. It's actually, yeah, the stress strain is like one line. You must clearly show that it's in one line. So yeah, so that's the feature of the cross section. And then I have something to note. The neutral axis, it's not the centroid. Those are two different things. So centroid is the geometrical center. So basically, if you have a rectangle, the centroid is basically in the middle because it's the geometrical center. Like the points are equally far away, you can say. So it's a bit low actually. So this is the centroid. This is h/2. However, remember RC is a composite material. It's consisted of steel and concrete. So the center of mass, not center of mass. Actually, that's sort of center of mass, but the neutral axis is not at the centroid. It's because it's a composite structure. Okay, it's steel plus concrete. Okay, I will explain how you will get the neutral axis again in the next page. But just take note that centroid and neutral axis in this case is different. Okay. Yeah, and then we have the strain and the stress graph. I think, yeah, you can see that. Actually, I forgot to explain the strain also, but I think it's straightforward also. So if you notice the top here, again, the topmost is the one getting compressed the most. So that's called the strain of concrete, or epsilon C. The line below it, it's actually one level with the center of the steel, the compression steel. So we label it as epsilon SC. It's basically how much the compression steel gets compressed. Again, the amount of compression, right, in the concrete and steel at one level is the same. So at this level, if the concrete is compressed that much, it's basically the same as the compression steel. So that's what it's basically what the statement says, the perfect bond. Yeah. And lastly, we also have epsilon S, which is the strain of steel, tension steel. Yeah, so if you notice, it's a bit higher than the bottommost level because the steel is located not at the bottom, it's somewhere above, right? It has a concrete cover, we say. Yeah, so that's epsilon S. Yeah, so that's the strain and stress. I think I'm done with this. Let's go to the failure modes. Okay, so there are three types of failure modes. There's ductile failure, balance failure, and brittle failure. This depends on the strain graph. So let's say you have a section, something like this. Okay, this is your section, then this is your steel. Okay, so I'll do only the bottom reinforcement, is the tension steel only. Okay, so so let's say again you bend it. So let's say this is your, okay, never mind. I'll draw the moment first. So let's say this is your moment. This is your M. So the top part gets compressed, bottom part gets tensile. Yeah. And then what do we do next? Let's draw the strain diagram. So this is new. Yeah, this is basically zero strain. Then of course the top gets compressed, so something like that, and then the bottom gets pulled. So let's start with ductile failure. What ductile failure means, right? Steel yields before concrete fails. So remember that concrete fails at what value? It's this 0.0035. So let's assume that the concrete has failed. So it means the strain at the top, since the top is the one getting compressed, right? So let's say the compression failure at the top, so it reaches compression failure. So this is 0.0035, basically epsilon Cu, let's say. So what ductile failure means, right? Like this steel, so at this steel level, steel already yields. So it basically says that at that level, the steel, right, is above this value, 0.00217. So it means, okay, let's go back. So it's something like this. Like this red line, which corresponds to this, like these three steels. This red line, the length is above. So this one is above 0.00217. So this is what it means by ductile failure. So I'll draw the line. So it goes something like this. Yeah, something like this. Let me rearrange some things so it looks nicer. Okay, something like that. Yeah, something like that. So this is called the ductile failure. So how about the rest? Okay, let's make this smaller. Actually, I'll do it on the, okay, I'll do it on the right. Okay, so for balance failure, I think it's as expected. So this is epsilon Cu. So this is 0.0035 as usual. We assume the concrete has failed. Then we check the steel. So the steel, right, for balance failure, like this strain length is exactly 0.00217. So that's what it means by balance failure. Okay, so that red line, that strain, right, is exactly 0.00217. So this is balance. Okay, I'll write it down. So this one is ductile. This one is balance. This one is brittle. The last one is brittle. So for brittle, again, the top we assume it's 0.0035. Okay, so like that. Then we assume that the strain, right? So this strain, I'll exaggerate it a little. So this one is still less than the yield strain, which is again 0.00217. So this is what brittle failure means. Something like this. Yeah, so this is brittle. Okay. So I hope this is quite straightforward. So we assume the concrete has failed, right? Then we check the steel. Has the steel yielded or not yet? That's how you differentiate ductile and brittle. Yeah. So why is this significant? Because to put it simply, if it's brittle failure, then it means that steel has not reached its full strength. Because remember, if you look at the stress and strain graph for steel, before epsilon y, the strength is low lah, basically. Like this is the maximum strength, but basically we are still here. So we don't want this. It means we are not using the steel enough. We just use concrete too much. Yeah. So that's why we don't want brittle failure. The steel has not been used, but the concrete fails first. And if that's the case, right, since the steel has not been used, concrete feels very brittle. That's dangerous. Okay. For balance, it means, yeah, steel yields exact timing as the concrete failure. So this is our middle case. For ductile, it means that steel strength has fully been used. Steel strength fully used. Again, if you refer to the stress and strain graph, ductile failures means steel is already here. Because the strain is more than 0.00217. Yeah. I'll highlight it. Okay. So that's why it's significant to have this middle case. Like this is the case that we're aiming for design line at least. So when we design for sections, we want to assume this. Second thing is, if you notice the position of the neutral axis, right? If you notice, ductile failures, the neutral axis is usually higher. Then balance is a bit lower, brittle is very low. And that's where this comes in. So if you notice, ductile failure, if x is less than 0.617d. So through similar triangles, you can actually check this out. If you want to prove, I can prove now also. But it's basically saying, remember x is the location of the neutral axis. So this is x. So for balance case, it's actually exactly 0.617d. So that's why we have this value, this random value, 0.617d. It's basically saying that's the neutral axis location that causes balance failure. So that's our borderline case. Yeah. If you want, okay, I can prove this very quickly, just for you to understand how we usually use the strain diagram. Let me do this. Okay. Okay, so D is, oh, I haven't explained also, I forgot to explain. There's X, D, and H. People usually mix up D and H. That's the common mistake. H is the full depth of the, full depth or length of the section. So it's top to bottom. For D, is from top to the middle of the reinforcement, the tensile reinforcement. So this one is D. Well, this one is H. Yeah, H and D lah. So be careful. There's also D prime actually, which is the top to the compression steel, but that comes later. The point is, balance case means concrete crushes when the steel has just yielded. So it's a borderline, we use the steel maximum power. Yeah. Okay, so let's prove for a very little bit. So if you notice, strain diagram will involve a lot of similar triangles. So get ready for that. So this is D, let's say. Okay. So let's use the similar triangles. So X divided by 0.0035. So I'm taking this length and this length, and I compare it to this whole length and this whole length. Because basically this is triangle. The triangle I'm looking at is this. Wait. is this. So that's D, and this is the base of the triangle, and then this is the triangle I'm looking at. Yeah. So it's equals to D divided by, wait, so D divided by 0.0035 plus 0.00217. Yeah, so again, the triangle are these and this. So these two triangles. Okay. So you can take up your calculator, but I'm pretty sure it's x equals 0.617D. So that's why it's called the balance failure. Let me check, just in case I'm wrong. Okay. So if we rearrange, right, so x is equals to 0.0035 divided by 0.0035. Yeah, so this is 0.617. Yeah, correct. 0.617. Yeah, so it's proven, yeah. So balance case is basically when steel yields and concrete crushes. Yeah. So any questions so far? This one again is still very theoretical, but you'll see the use soon. Okay, so no questions so far. No worries. Okay, we have ductile, balance, brittle, and proving. Then okay, you can just go to the actual section analysis. Okay, so for moment capacity, it's actually the total moment about the centroid. Again, not about the neutral axis. It's about the centroid, h/2. Okay, so it's about here, around here. So how you find the moment capacity is basically you take the moment of the forces about the centroid. So basically, let's say this is D1. Let's not use D. Okay, let's say use A. This is A, this is B, this is C, let's say. So by right, what you should do is FST. So okay, so moment is FST multiplied by A plus FC multiplied by B plus FSC multiplied by C. Yeah, so just take moment about the centroid. It's so if you notice, right, the value of ABZ is very tedious. You need to do some maths. It's very tedious. This is what you actually need to do if it's in column. You need to find the ABC. No, this is just to give you some context first. To like this. Yeah, just take moment about the centroid. However, for sections subjected to pure bending, there's a exception case. So pure bending means there are no axial force and it's usually beams. Some beams are subjected to axial force, but usually very little. So we assume no axial force. Okay. Let me drink for a while. uh, ah, okay. So for pure bending, we can use what is called by the couple moment. So again, this is an MOM review. So there's a lot of MOM involved here in the stress and strain, and also like forces and moments. So to review couple moment, it's basically two forces. So let's say this F, this F. So exact magnitude, so same magnitude, both are F. And then they are exactly the opposite way. So if one goes up, one goes down, one goes right, one goes left, something like that. Let's say this is D, the distance between them. The perpendicular distance between them is D. So this is called the couple moment. So what it means, right? If you have forces like this, no matter where you take moment at, right, the moment is always F times D. So what I mean by this, right? So let's say I want to take a moment about A, let's say. Okay. A is arbitrary, okay? So I'll use X here, a variable. Okay. So this is X, that's A. So if you notice, if you take a moment about A, right? Again, this is MOM review. So what's the moment by this force? It's basically the force multiplied by D plus X. Okay, because the force goes this way, clockwise positive. While the other force, so this is the force. What's the moment? The moment is just F times X. So it's again this force, right? I'll make it red so it's clear that it's a force. So this force, this is force. So one goes clockwise, one goes anti-clockwise. So it's a minus F times X. And that becomes F times D. So if you notice, the X is gone. Like this X is gone. So it means doesn't matter where you put A, the moment is always F times D. Okay, this is called the couple moment. Okay, again, this is MOM review. This is called the couple moment property. So write it down. So no matter where you put center of rotation A, the moment is F times D. That's a couple moment property. Something that you might have seen in MOM also, right, is, so let's say you have a beam, then sometimes you see like the prof gives something like this, this is 20 kilonewtons meter. This is actually this. So if you notice, right, when you apply, let's say, moment about A, right, let's say this is A, you also need to include 20. And let's say you take a moment about B, right, MB, you also need to include 20. So no matter what the point is, right, you need to include it, like this arrow. Yeah, the reasoning is actually this. Yeah, again, this is very theoretical, but I'm just saying that for a couple moments, no matter where you take moment from, right, the moment is always F times D. And now let's see how we can use this property for our RC section for beams only. For beams only, columns, I think you cannot, unless there's no normal force. Okay, so let's go back to this diagram. I'll redraw it actually. So let's say you have a section. Then you have the, oh yeah, I'll assume the steel has yielded, just for simplicity. Later we will see the one if it's not yielded yet. Okay, so you have the concrete force here. So this one is in compression. Yeah, again, this is 0.8x. Okay, they don't need this. Let's say this the force of concrete. Oh, let's assume we have compression steel as well. So let's say FSC. Then we have FST, the tension. Okay, so we need to take moment about the centroid just now, right? Okay, so of course I'm not going to do the long way. I'm not going to do this. This will take a very long time. That's why I put the ABC. Actually, I put it in my cheat sheet. I will share with you once the quiz comes. Yeah, but for beams, right, you can use the couple moment property. So what this means, right? First things first, the force is actually balanced. Okay, the force is actually balanced. So FST is FSC plus FC. So the tension by the bottom steel is equals to the compression of the top steel plus the concrete. This is just basic force equals zero thing. Yeah. So if you notice, since there's no normal force, again, there's no actual force for pure bending, you can actually split this arrow into two. So what two is just FSC and FSC lah, because again, FST is just the total of the two. So I can redraw this diagram as something like this. So unlike this FC, and I have FSC. And then again, FST is just the sum of the two, right? If there's no axial force. So actually you can redraw it as something like this. So this is actually the same as this for pure bending. Right? Because again, FST is just the combination of the two. Right? So if you notice, we have two sets of couple movements, one going right, one going left, correct? So the first couple movement is the FC, the second couple movement is FSC. So again, I know that we need to think about the centroid, but for couple movements, we don't care about where we take the moment. We don't care whether we take the moment. So it applies also for the centroid. So again, what's the moment then? Remember, we have two sets. So let's name this Z2. Let's name this Z1. So the moment about the centroid is actually just FSC multiplied by Z2 plus FC multiplied by Z1. So done. Very simple. You don't need to find ABC anymore. Because if you don't have a couple moment, right, you actually need to know the distance. So let's say you have a force and you have a point A, let's say. And let's say this is point B. Of course, the moment at A and B will be different. The moment at A is F times distance 1. The moment at B will just force times distance 2. So this distance 1, this distance 2. Yeah, so you see the difference? So this one is just a simple moment from a force. This one is a couple moment. Okay? So I hope you're getting this. Because if you go to the tutorials, some of the prof will actually teach you directly the couple moment method. And then later in columns, they teach something else, which is actually the general case, the ABC. So this is just to get you clear. Where does the calculations come from? So the general case is actually just to take the centroid. So this is the general case, is to take the moment about the centroid. But for pure bending, we can use the couple moment property. So the calculation is much simpler. Okay, so any questions so far? I'll zoom out. This is the toughest section of the. Oh, this is the second toughest. The toughest is still like the yield or no yield, but that one is later. But I hope you understand this first. This one is very important. And let me drink first. Okay. Okay, so if no questions, then I can continue. So actually, it's already the question section already. So yeah, this actually copy pasted from my cheat sheet because I'm just showing it the important parts here. So if you notice, this is how you do the section analysis for beams. So first step is to assume that all steel yielded, because yielded is usually the case, the ductile failure. Like all designers, they try to have all the steel yielded. That ductile failure. Okay. Then flange beam, I'll cover flange beam later. But let's go to the second step. We check if the failure mode is ductile. So again, we need to see the strain diagram. We assume that the concrete has crushed. Then we check the strain of the steel. So that's the second part. Actually, sorry. We just checked the D is enough already. Yeah, because again, we have this calculation, the proving, right? So if you know the location of the D and X, then easy loh. Yeah, so we compare the X and the D actually. Yeah. So that's the second part. The third part is calculate M, the moment capacity. The moment capacity is the one that I just explained just now, the couple moment property. This thing. Okay, so we just go to the question. Actually, sorry, not yet. I'll explain this first. So, let's go to the singly reinforced rectangular. I think it's easier. So I think again, I'm referring to MOM. Stress is force divided by area. So if you want the force, it's basically the stress multiplied by area. So these are actually this. So the stress of concrete. So if you go back again here, where is it? Here's the stress of concrete, 0.567 FCK. That's the stress. So FCD here is actually sigma CD. Yeah, but it means the same thing lah. So yeah, that's why it's 0.657 FCK. So this is the stress. This second part is the area. So if you notice at this thing, again, the one in compression is this for concrete. I'm talking about concrete first. So it's basically just the breadth of the section. You multiply by the 0.8x because we assume compression only happens for 0.8x. So yeah, that's the area of the concrete. For steel, similarly, again, this is assuming that all steel has yielded. Okay, it's 0.87 FYK. So that's the strength of the steel that has yielded. You multiply by the total area of the steel. So this area. So you see those three circles? Yeah, you just add the area. Yeah, those are the forces. Next is we have the setup. So this one is actually just the what's that? The force equilibrium. So again, it's this one. Yeah, so depending on the reinforcements, if it's singly reinforced, it's just the tension steel and concrete. For double, it's FST and this. Yeah. So the one that I show you just now is the proving for double. Okay. Next is find Z. Again, we just need to use the couple moment. We don't need to calculate the distance to the centroid. So Z here, or Z1 or Z2, is actually the couple moment arm. So it's actually this image I'm showing just now. We have two sets of couple moments for double reinforce. Okay, so that's how you read like the formulas. Okay, I'll just write it down. So this is force equilibrium. This one is the couple moment arm. This one is just force times, yeah, it's this lah, F times D. Or this, same thing. Yeah, couple moments. Yeah, well, this one is the couple moment. So that's everything actually for theory. So I hope you see the logical pathway lah from the beginning that I explained, from why is it RC, and then stress and strain, and then combine lah the strain and stress and strain. Yeah, so again, this is force sigma is stress times area. Yeah, so it's a bit more complicated for flange beams, but we cover that soon. Okay, so question you can do with me. Actually, my plan was to like leave and ask you to do first, but since this is recorded, I might as well just do together. So yeah. So as a checker, you are given the design for critical section at mid-span, blah 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 blah. Okay. So the moment in demand is 120. And determine whether the design is adequate. So concrete class is C25, steel bars grade 500. So I'll try to not to cheat this. I'll try to explain it in terms of, again, the basic principles. Okay, first of all, we are acting as a checker. Checker means we have the section. So we have the area of the steel. We have the concrete sections, area concrete. And based on this, we need to find the moment. So this one is checker. For designer, it's the other way around. We have the area of concrete also, the section of concrete, but then we only have the moment. So based on this moment, so in this case 120, we are asking what's the minimal amount of steel. So that's designer. So those two are two different inputs and outputs. For checker, you have the section, you have the steel already. Then you want to find what's the moment it can handle. While for designers, okay, I have this building. My architect say, okay, I want this beam to be able to hold this much moment. Then you as a civil engineer, you ask, okay, sorry, you are trying to discover what's the area of steel to hold that moment. So this just for context. Today we're going to do checker only because designer is even easier. It's just follow the steps. Legit, just follow the steps. Yeah, so we do checker because checker a lot more theory. Yeah, because all this is checker. Yeah. So let's start. So actually never mind, I'll cheat. So all steel has yielded, right? So okay, first of all, we draw the section. So 1, 2, 3, something like this. Then we have 250. Then we have H is 400. D is 360. All of the dimension in mm. Next is we draw the forces. Actually, you don't need to draw actually, if you know. But again, I'm showing the basic principles. That's why I draw. So this is your stress diagram. So the top part will get compressed. Something like this. So this FC. The bottom part will get tensile. So this is F, ST. Okay, next is the equilibrium of forces. So FC is equals to FST. Okay, so what's FC? Again, it's the stress times area. Again, the area for concrete, we assume it's 0.8 x. X is the neutral axis. So again, stress times area. Stress is 0.567 or 87. Maybe I should. Oh, 567. The stress is 567 FC. Okay, that's the stress. The area, we're talking about this area. This area. Okay, so that's B 250 actually, 250. Oh, actually, we know FCK also. FCK is 25. Okay, never mind. I'll just write B first, so it's not confusing. B times 0.88, so 0.8 x. So that's this blue area. Equals to the force of steel. Again, it's stress times area. Stress is 0. Oh my gosh, my memory. 87. 87 FYK. You multiply by the area of the steel. So that's AS. And that's it, because we only have tensile steel. Yeah, tensile steel only. Okay, next is we just plug in the value. 0.567 FCK in this case is 25 multiplied by D 250, 0.8x, and 0.87 FYK is grade 500 multiplied by area of steel. Here 3H20. 3H20 means oh yeah, okay, yeah. Again, these are just naming. So 3H20 means 3 bars of high grade steel diameter of 20 millimeters. So that's the meaning. So the H came from high grade. High grade. It used to be T, so sometimes you see like something like this. It means the same thing. I forgot what T stands for, but I think it's tensile. I'm not sure. I might be wrong. But it used to say tension T, sorry. Yeah, it used to say T. But it means the same thing, huh? Okay, so what's the area of the steel? You can actually they actually have a table. You can actually check that, but you can also find manually. So area of circle, so area of circle is just 3 times pi over 4 diameter squared. Then we just solve for x. So left side 0.567 times 25 times 250 times 0.8. 0.567, 25, 250, 0.8. So it's 2835 is equals to 0.87, 500, 3 pi over 4, 20 squared. 40997778 lah. It's a very big number. Oh, by the way, I forgot to mention something. This one we assume the steel has yielded. Okay. So I'll write it down. Assume steel yielded. Okay, so next x is just so the divided by 2835. 145. So 145 millimeters. So that's our neutral axis. Okay, so let's just go to the next part. To find the moment capacity, again, we use the couple moment property since this is pure bending. So what we can do, again, we have two forces only. We just need to find the moment arm, Z. Okay, so if you notice, this whole thing is D. Then this small thing is basically half of 0.8x. So 0.4x. Correct? So the from the couple moment property, so moment is equals to FSE multiplied by Z. Or you can do FC multiplied by Z. It's both the same thing. Since again, this FC is equals to FST. So both can. Okay. So in this case, I'll use the FST as an example. Which one is easier? FST lah. So 0.87 multiplied by FYK, in this case is 500, multiplied by, again, this area, 3 times pi over 4, 20 squared. So this is FST. Again, it's stress time area. Multiplied by the arm length. In this case, it's D minus 0.4x. So D minus, okay, already D is 360 minus 0.4x. So I'll write it in gray. So this is D minus 0.4x. Okay, something like that. So we just calculate. What's the unit? I might be wrong. I think you need to divide by 1000 again, but let me check. So 0.87, 500, 3 pi over 4, 20 squared times 360 minus 0.4, 145. You will get, well, is it very big? So you multiply by, I think 10 negative 6. So 1, 2, 3.8 kilonewtons meter. I'm too lazy to figure out the units. You figure out yourself. Because like this is millimeters squared. Is Newton per millimeter squared. Oh, sorry. Yeah, millimeter squared. Yeah, so it's millimeter, then you have to turn. Yeah, it's correct. It's 10 minus 6. Yeah, so that's how you find it. So quite simple. So all cases is actually like this. I'm just showing it in terms of basic principles. That's why it's quite long. But actually you can just copy paste this. Because this came from this. Yeah. So let's go to the next one. So this one I purposely oh, For the next question, I purposely use the one that is not yielded, so y'all can know. Oh, by the way, how do you know if the thing is yielded? I forget to, before you find the moment, right, you need to check if the steel has yielded or not. So it's, if it's X145, right, you need to check with this. So 0.61, okay, so what's 0.617D, right, is, what's 0.617D times D360 is 222. So that's less. If it's less, then it has yielded. Yeah. So steel yielded. So this one is okay. So our assumption is right. Okay. Yeah. So done. Let's next question. So you have a checker. You are given this. Blah blah blah. Oh, by the way, I forgot to answer the question. The moment in demand is 120. Then we get 123. So this one is bigger than 120. So this one is okay. Yeah, but that 120 is not really important. The important part is the moment capacity. Yeah. Next. So this one is concrete class 32, steel bars 50. So same question. So let's do it very quickly. So first step is to find the stress diagram. Again, this is just for showing. FC, FST. Then let's do FC is equal to FST because there's no compression steel. So FC is 0.567 FCK multiplied by the area. So that's V times 0.8 X. That's equals to FST, which is 0.87 FYK. That's the stress times the area of steel. So 0.576. FCK is 32. V is 200. 0.8 X. Then we have 0.87, steel 500. Then pi over 4. 3 times pi over 4. 3 times pi over 4. 25 squared. Then use your calculator. 0.567, 32, 200, 0.8. It's 2903. 2903 means equals to 0.87, 500, 3, pi over 4, 25 squared. That's 640,590. Yeah, done. So X is just 221 millimeter. Again, this one is under the assumption that the steel has yielded. Okay. Assume steel yielded for this. Again, we check our assumption. So what's 0.617D? That's how we check. 0.617D is D is 3110, not 350. Be careful. 191. And if you notice that X is bigger than 0.617D. So what this means, it's a brittle failure. Okay, and steel has not yielded. So steel has not yielded. So in real life, if we found out that the steel has not yielded, we just say to the designer, hey, this one is brittle failure. You need to redesign, right? Increase the steel. Hey, sorry, increase the steel or decrease the steel? Shoot, never mind. But anyways, yeah, you just say to your designer, okay, this is brittle failure, I don't want this, redesign. However, for this question, we just, okay, if you let it as it is, what's the moment capacity? Okay, so let's figure that out. So first of all, of course, we cannot just simply do this. Why? Because, again, 0.87 FYK is only if the steel has yielded. If it has not yielded, again, let's go back to the first line. If the steel has not yielded, the strength is just the Young's modulus multiplied by strain. Yeah, again, the stress and strain relationship. So let's go back. So in this case, you need to find the neutral axis. Wait, let me think. ES times strain of steel. Okay, so in this case, you need to draw the strain diagram. So something like this. Then something like this. Is 0.00315. 0.0035, I think. I forgot what's the value. Let me check. Yeah. Yeah, 0.035. 0.035. Yeah, and then this red line is less than 0.00217. So we need to find that manually. So we have D. D is 310. K. So something like that. So how do you find X? So it's basically saying, okay, so what's this string first? Again, we use similar triangles. Again, the triangle I'm looking at is this and this. Okay, so this one is X. This one is the strain of steel. So X divided by 0.0035, which is the small triangle, this one, is divided by 310. Sorry, is 310 divided by this 0.0035 plus ES. Okay, so in the end, you will get from rearranging, right? So 0.0035x plus ESX is equals to okay, 3110 multiplied by 0.0035, so that's 1.085. Okay, then through some rearranging, we will get ES is equals to 1.085 minus 0.0035x divided by x. I might be wrong, but this one should be correct. Let me check. Yeah, should be correct. Should be correct. So yeah, so if you notice, right, if the steel has not yielded, the calculation is much longer. But usually don't need to worry. Usually they test the yielded only. Unless it's column, then column you might need to do this. That's why it's important for me to convey the basic principles first. So you'll not get confused during columns. If you know this, right, columns easy one. It's just like legit what you did, what you need to do, right? For columns, you just need to take to the centroid. The second one, it's not just this. There's a normal force, something like this. So it becomes like FST is FC, FSC plus N. That's for column later. Yeah, but for now, we talk about beams. Okay, sorry for the sidetrack. Okay, so yeah, so again, the logical way to think, right? So you calculate assuming the steel has yielded, then you check has it actually yielded according to our assumption. If it's not according to our assumption, then this force is wrong now, basically. It's not accurate. So that's why we need to do it again. So FC is equals to FST, just like the one before. So the left side is actually exactly the same because concrete, again, there are no cases for concrete. It's always the same. The right side part is different. Again, what's the stress? The stress is the strain multiplied, sorry, the Young's modulus of steel multiplied by the strain of steel. So this one is the stress multiplied by the area. So it's still AS. So again, okay, I'll put this down so it's not confusing. Something like this. Then this one. Okay. So ES, there's a set value. According to Eurocode, it's 200,000. In steel design, they use 210. But in this course, I think you can just use 200,000. Yeah. Then ES, again, we just substitute from this. So we substitute. Yes, it's very long, I know. So this copy, then paste. Then you multiply by area. So this area. Okay. Then you just solve for x. Yes, it's a very long process. So I hope you know how to use the solve function in your calculator. If you don't know, you can try to Google, or I can send you the PDF. Is the solve function, so it will solve the equation for you. Okay, but for simplicity, I'll just directly tell you the answer. So let me type it out in my calculator first. So 2903 x is the left side, so that's equals to, the right side is 200,000. Then you multiply by 1.085 minus 0.0035x divided by x. Then the area of steel. Oh no, I messed up. Let me retype. 2903x is equals to, again, the right side, 200,000. 1.085 minus 0.0035 x divided by x. 3 times pi over 4, 25 squared. Then solve. Let me put the value as 190. Let's see what we get. You'll get 198. Why is it 198 then? I might made a mistake somewhere because it's still more than 191. So something should be wrong. Okay, but oh my gosh. What's Oh no, 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 it's correct, it's correct, it's correct. It is brittle failure. It is brittle failure. Yeah, yeah. So it is still bigger than the balance case. It's just this one, we have the correct value of the force. The force we need to use ES epsilon S. We cannot just use 0.87. Again, it's because of the yielded and not yielded case. Okay, so X is that. And then after you have X, then you can just do the next part, which is the couple moment. So for this one, the couple moment, of course, we don't want to use steel. It's a bit scary to use steel. It's very complicated. So let's just use the concrete. So the moment is the force of concrete. You multiply by Z. So force of concrete is 2903x. Yeah, it's basically this thing. This thing. So 2903 times 198 times. So Z again, Z is just D minus this one. So this one. Z is just D minus 0.4 x. So in this case, I'll just use D. D was D. D is 3110 minus 0.4 times x 198. So you will get 2903 times 198 times G110 minus 0.4 198. So you will get, okay, again, multiply by 10 minus 6. Okay. So you will get 132.7 kilonewtons meter. So this one is 135, this one. So still less than 135. So not okay at all. It's a brittle failure and it doesn't meet the moment capacity. So no, not okay. Ew. So any questions so far? This is actually might be the most confusing part. Yeah, this is the hardest part, basically. If you understand this, you can understand columns already. Because it's just the same thing. Let me see. Okay, no chats yet. So, okay, I guess no question. If you're confused, you can replay the video. So, I'm pretty sure the pathway is already logical. So, if you are confused, you need to go back to the theory part. Okay. So, that's for not yielded sections. Okay, we have like around 14 minutes left. I think we can do one more question and we're done for today. So, I'm just want to cover on the T-beams. So, again, the concept is the same. So force equilibrium and everything. The difference is, if you look at the section, there are two cases for flange beams. Again, remember that if you draw the what the stress diagram for concrete, right? So this FC, let's say. This one is 0.8 x. So if you imagine there are two cases, 0.8 x can be here or it can be here. So if it's below the flange, so basically the long case, the compression, right, is all of this. So that's for the first case. It's below the flange. So this is 0.8x now. The second case, it can be also something like this. So this is 0.8x. Then in that case, the compression is just this. So there are two cases for flange beams. So let's try. But the concept is exactly the same. It's just there are two cases, 0.8x you need to compare. Okay, so you have, okay, as a checker, you're given a design, moment demand. So you have concrete class, 25. Then steel bars grade 500. So let's just do it very quickly. So for flange beams, I've written here, assume that the neutral axis is below the flange. So HF, yeah, HF in, yeah, this HF is this one. This is HF. Okay. So let's just do it very quickly. Okay, so okay, I'll explain this thing first. Okay, if you notice, this is the one that I told you before. These are the stresses. These are the areas. Okay, so force is just stress times area. For flange, we divide it this way. So again, this is the case where the neutral axis is below. So it's somewhere here. So you look at this as the compression. So we usually divide it to two, FCW and FCF. It's basically the force of concrete in the web and the force of concrete in the flange. So this image represents that. So I'll use red. So FCF is both of these combined. FCW is this. Okay, let's start with FCW. Okay, so FCW. Okay, assume S is, okay, S is 0.x is the neutral axis, by the way. Zero, not neutral axis, sorry. S is the concrete stress block. Yeah. 0.8x is S. Yeah. So this one is bigger than HF. It means the compression is until below something like this. Okay, so that's always the first step. We will, again, as usual, if we make assumptions, we need to check later, just like the yielding and not yielding part. So FCW is, just follow the formula, 0.567 multiplied by FCK, 25, 0.8x. Then BW, what's BW? BW is 300. Is the breadth of the web. Yeah, so this is this BW, this one is BF. So the breadth of the flange is the whole thing. Breadth of the W is the web, the middle. Okay, so this one is something we will calculate later. So FCF, again, if we're taking these two combined, right, it's basically the whole length minus the BW. That's why the formula is BF minus BW. Yeah, because we're taking the sides only lah. So we just minus the whole thing with the middle. So 0.567 multiplied by FCK, which is 25. Then HF is just now is what? This one, 65. 65. Then BF minus BW. So BF is 1,200. BW is 300. So okay, let's put it inside our calculators. It's 3,400. This one is 65. It's 0.567, 25, 65, 1,200 minus 300. So you will get 829,237 or 8 lah, yeah. I just round up. Okay, of course we have the steel below. So F steel intention, yeah, but F or FS is same thing now. So that's 0.87 steel grade 500. So that's the stress multiplied by the area. So the area is just, oh, there are 8 lah. So 8 times pi over 4, 25 squared, the area of a circle. So that's just times 8 times pi over 4 squared. Yeah, 0.87 times FYK 500 and 8 pi over 30. So you'll get 170,8241. Yeah, it's a very big number. Okay, so we do the equilibrium of forces. This one I've written it here. So this one is tensile, the rest is compression. So Fs is equals to FCF plus FCW. So 170,8241 is 3402x plus 829,238. So x is, okay, let's calculate. 829,238, 3402. So it's 258. Okay. So actually there are two things that you need to check. First thing is the concrete first. So 0.8x. Okay, check assumption. So check assumption. So S is 0.8 multiplied by 258. That is 206 millimeters, which is above HF. HF just now is just 65. Okay. So assumption is correct. So assumption, okay. Assumption for concrete, okay. Because it means that our assumption of it being until like this, right, is correct. Okay. Next one is, of course, the steel. So for steel, yielding, right? Yielding. So again, X is 258, right? Then 0.617 times D. D is what? D is 865. Yeah, already done. So D is 865 mm. So 0.617 times 865. 533. So this one is less than that one. So this one is okay. So assumption for steel is okay because it has yielded. Okay, so assumptions are both correct. So we just continue on. So again, the moment is just we can just use the couple moment. I'll use the steel F times Z lah. Okay, so steel just now FST is what? This one. 170,8241. 1708241 multiplied by z. So z is 0.4x, right? Sorry, d minus 0.4x. So d, so 865 minus 0.4 times x. X in this case is 258. Then we multiply by 10 minus 6 kilonewton meters. Okay, so what do we get? 1708241 times 10 to the negative 6. So 1,300. You get 1,301 kilonewtons meter. So the design is just 1 to 50 lah, so bigger than 1 to 50. So if you notice, we are done. So just on time, exactly 1.5 hours. That's the target actually. Yeah. So if you notice, I haven't included double reinforced concrete, but it's exactly the same. So that's why I don't include it because it's the exact same thing. We just have an extra FSC here. Yeah. So yeah, just plug in is exactly the same. I won't even explain it in the next session actually, since it's exactly the same lah. My point here that I'm trying to make is just the yielding of the steel and also this one, the flange. Yeah, so that's the whole session, I guess. I think there's not much else I can say. I will cover this and I will go back to this topic during columns, because columns is exactly the same as this. Yeah, just with a normal force. Then in this case, we have a harder moment arm. Like moment arm, you need to find one by one instead of couple moments. So okay, I guess I'll do a very quick summary. So we covered RC, like what's RC, what are the assumptions. The assumptions at least you need to know. I don't know if they will test it again this year. I see how. Then we covered the stress and strain. So for steel, there are two cases. It has yielded or not yielded. We assume there are like two lines only lah. So yeah. Then we have concrete. For concrete, there are no cases. It's always the compression. Tensile, we assume 0. That's why there's no, like the bottom is 0 lah. We only take the 0.8x. Okay. Yeah, again, and then of course the x, if x is a neutral axis, then the strength is just 0.8x. Then we covered this, all the stress and strain, and then the cases, the failure modes. Yeah, again, similar triangles is very important in this topic. Only when the steel has not yielded only. If it has yielded, then you don't need to do all the similar triangles. But in columns, you might need. I think you will need actually. You will need in columns. So that's why I teach you now. Then we reviewed the couple moments, why it can be used in the beams, but not columns, because columns we have N, like the normal force. That's why we cannot use the couple moments. Yeah, but beam you can. Then yeah, we covered how to get the moment capacity lah. So yeah, are there any questions? Yeah, if not, then I guess that's it for today, I guess. Yeah. So if you have any questions, just text me lah. Yeah, thank you for three of you for coming. Sorry for being late because again it's the bus being late. Yeah, the charter bus being late lah. Yeah, so yeah, so I guess that's all. Again, I will put this up on the same folder as last week. Yeah, so this one is annotated. Yeah, annotated. Okay, so if there are no questions, I guess I can end the meeting. I'll stop the recording now.